Hi everyone! So last week we talked about simple machines and how they help us do work by amplifying force, meaning that the output force is greater than the input force. We learned that there are 6 types of classical simple machines: the inclined plane, the wedge, the lever, the wheel and axle, the pulley, and the screw. We also took an in-depth look at the wheel and axle, wedge, and pulley. This week, we're going to be looking in depth at the other 3 types of simple machines: inclined planes, levers, and screws. Next up, we've got inclined planes. An inclined plane is simply a flat surface that's at an angle relative to the ground, so it's helpful in enabling us to move heavy objects. Inclined planes are super common in everyday life. There's 2 examples here, one of a wheelchair ramp and one of a ramp for offloading from a truck. But try and think of some other examples that you see in your day-to-day life. Another cool thing about inclined planes is that 2 other classes of simple machines can be considered a type of inclined plane. Take a moment to think about which ones those might be. The first simple machine is a wedge, which can be thought of as 2 inclined planes pressed together. And the second one is a screw, which can be thought of as an inclined plane wrapped around a cylinder. So now we know what inclined planes are and that we see them in everyday life, but why do we see them in everyday life? Why do they help us so much? Well, to answer that question, let's first think about what happens if we don't have a simple machine. Take this stick figure, for example. It's trying to lift up the box off the ground. And what forces are in play here? Well, first, there's the force of gravity. Gravity is always going to pull the box towards the ground. So we can mark it with a down arrow, just like this. So to stop the box from hitting the ground, the stick figure needs to apply a force upwards so that gravity doesn't pull it all the way down. And we'll indicate that with a green arrow going up. And now, in order for the box to keep moving upwards, the green arrow needs to be greater than or equal to the force applied by gravity. This means that the force that you're pushing up on the box has to be at least as strong as the force of gravity on that box. Now, let's think about that same situation, but this time we have an inclined plane. Gravity is still going to be pulling down on the box, but instead of applying force straight up to oppose gravity, you're applying a force this way. And at the same time, the ramp is applying what we'll call a normal force upwards on the box. That's that green arrow that you see that's at a 90-degree angle to the ramp. So these forces are working together to oppose gravity. When you have the normal force and your applied force of the push that you're applying working together, you don't have to work as hard to oppose the force of gravity, since the inclined plane is helping you do that. This is how an inclined plane allows you to move something up to the same height while applying less force. However, we know that the amount of work has to be the same. So the reason that we're allowed to apply this less force is because it's over a longer distance. This side of the triangle that I'm underlining in red is much longer than if we were just to lift the box straight up. That's in blue there. So if we think about work equaling force times distance, with an inclined plane, which we'll write in red, the force is lower, so the distance has to be greater. That way, the amount of work that you're doing is the same, even though you're applying less force. Last week, we talked about how all simple machines have a property called mechanical advantage. We also said that mechanical advantage was a ratio between 2 things, so its numerical value is one thing divided by another thing. Can you remember what those 2 quantities are? The mechanical advantage of a simple machine can be defined as its output force divided by its input force. So, if you were to input 2 newtons of force and end up with 6 newtons of force outputted by the machine, the mechanical advantage is 3. Now let's think about what mechanical advantage means in terms of inclined planes. In this case, output force can be thought of as the amount of force that it would be required to lift the box straight up. And the input force is the amount of force you're actually applying to push it up the ramp. Before we go to how we can define an equation for the mechanical advantage of an inclined plane, take a look at these 3 planes. Try and rank them in terms of their mechanical advantage, from least to greatest. In this case, we can kind of think about mechanical advantage as how hard it's going to be to push the object up the ramp, as in, how much force are you going to have to apply? Well, the steeper a ramp is, the harder it's going to be to push up. So we can say that a steep ramp has a really low mechanical advantage, so we'll put number 1 at the lowest, since it's the steepest of the 3. The next steepest is number 3, so it goes right in the middle. And number 2 is a very shallow ramp. That means it wouldn't be that hard to push something up the ramp, but since it's so shallow, we're going to have to push it up a really long distance to get it to the same height. See how the length of the ramp in 2 is already longer than the length of the ramp in 1, and it doesn't go up in the air nearly as high. You'd need a really long ramp with a high mechanical advantage to push something up to the same height as a ramp with a low mechanical advantage. But the benefit to it is you can apply a lot less force to push it up that greater distance. Now that we have a conceptual understanding of how the steepness of a ramp affects its mechanical advantage, let's talk about how we actually define mechanical advantage as a formula. We can say that the mechanical advantage of a ramp is equal to its length divided by its height. This means that if a ramp is 4 times longer than it is tall, it's going to have a mechanical advantage of 4. This means that you can apply 1/4 of the amount of force that you would need to lift it straight up, but you would have to apply that force over 4 times longer of a distance. Something really important to consider when you're thinking about the mechanical advantage of a ramp is the force of friction. The definition that we gave earlier is what's called the ideal mechanical advantage. That's if you had no friction on the ramp. However, when you're pushing an object against something, friction will work against you. Think about when you rub your hands together and they warm up. That's because friction is doing work.
Hi, my name is Shannon and I'll be talking to you guys about levers. Levers are some of the most important simple machines around. They're everywhere. For example, have you ever played on a seesaw with a friend? Well, a seesaw, otherwise known as a teeter-totter, is a type of lever. A lever is a simple machine that has a long beam or rod that rests on a support, called a fulcrum. This fulcrum is where the lever pivots. The load is the object that is being lifted or affected. In a seesaw, whoever is being lifted up is the load. But in order to lift a load, there has to be a force acting down upon it to move it. That force, such as the kid pushing down on the seesaw, is called the effort. There are 3 types of levers. In each of them, the effort, load, and fulcrum are in different places. A first-class lever has the fulcrum in between the effort force and the load. You push down on one end, and the other one raises up. If the fulcrum is in the middle, like on a seesaw or a balance scale, otherwise shown like this here, then to lift 10 pounds of weight, you need to apply 10 pounds of force. The effort and the load are the same. And because the effort and the load are the same, the lever doesn't let you lift anything heavier than you could normally lift, and there is no mechanical advantage. However, if you place the fulcrum very close to the load and have a long bar to press down on, This gives you a mechanical advantage. It makes it easier to lift the load. For example, 5 newtons of effort could result in lifting 10 newtons of the load. You might do this if you had a very heavy load to lift, such as using a long lever to pry up a large rock. Some examples of first-class levers include a balance, a teeter-totter, or a seesaw, and also scissors. A second-class lever is one in which the load is in between the fulcrum and the effort. The best example of this is a wheelbarrow. You lift up on one end, and the fulcrum rests on the ground. Another example of this could be a bottle opener, where the fulcrum tucks under the edge of the lid and one end of the bar rests on the lid. The most common example of a second-class lever is a door. You push on the handle to move the door. The fulcrum is where the door hinges, the effort is the handle, and the load is the entire door itself. You've done this plenty of times before. When you open a door by the handle, it's easy, right? But have you ever tried pushing it open closer to the hinge or the fulcrum? It becomes much harder. Try it at home. This is because you have less mechanical advantage when you push closer to the hinge. A third-class lever is one in which the effort happens between the load and the fulcrum. A common example could be a hammer. A hammer acts as a third-class lever when it's used to drive in a nail. The fulcrum is the wrist, the effort applied through the hand, and the load is the resistance of the wood, which is right here. A fishing rod is also a third-class lever. The load is the big fish at the end of the line and the top of the rope. The beam is the rod itself, and the force is the person reeling in the fish using the rod's handle between the two ends. The fulcrum is the bottom part of the handle of the rod. Now, I have a question for you guys. Can you think of any other levers that can be found in your house?
I'll be talking to you guys about screws. Think about opening or closing a water bottle. Notice how just by turning the cap lid, you're able to move the water bottle cap up or down. How does this work? Well, it works because of a simple machine called screws. You probably think of screws like these things as they are turned to make the screw go into wood to hold things in place. That is one example of how we use screws to convert rotational motion into downwards motion. Rotational motion is like moving the head of the screw around and around, and then we get downwards motion or forwards or backwards motion as we move the screw somewhere with this rotational motion. So what are the parts of a screw? Well, we first have the shaft, which is this long cylinder shaft, which is kind of like the body of the screw. Then we have the threads, they're the ridge that runs along the whole screw. And then we call the pitch is the distance between each thread on this shaft of the screw. Now, how do we use this to figure out the mechanical advantage of a screw? Well, simply put, the mechanical advantage of a screw is the circumference of the shaft divided by the pitch. So let me explain what a circumference is. Basically, let's say that we have a circle. It's a badly drawn circle, but basically the length of this blue line, or the outer edge of the circle, that length is the circumference. So we're looking at the circumference of the shaft divided by the pitch, the length between the threads. So, now let's see how this works with two screws that we have here. The right screw has a higher mechanical advantage because the pitch is smaller, like the threads are closer to each other. And it makes sense. With less force, we can move the screw down. It will take more rotations around and around, but still it'll take less force for us to take the screw and move it into the wood. However, with this screw on the left, it has a lower mechanical advantage because the pitch is greater and the threads are farther apart. Here, although it'll take less rotations, it'll take a lot more force to get this screw into the wood. You might think, why? Why do we need more force with the screw on the left? It's because since the threads are farther apart, with each thread, we're moving farther into the wood, so it takes more force on our part to move the screw farther into the wood. What are some examples of screws in our lives? Well, of course, we see screws like these, which are used to hold things together. We also talked about water bottle lids acting like screws, and lids of other containers like jars are often screws. We can also use screws in things like clamps, which convert the rotational motion into forwards motion, or downwards motion here, to hold something in place. Can you think of any examples in your lives where rotational motion is converted into forwards or backwards motion with screws? Thank you for listening and have a great day.